Let's welcome everyone, right? Welcome to the show. We have a good team. We have Ivan, Chris, David, Yannick, and Alex, and myself, me. So we again prepared 4 questions, and we hope to discuss all of them. And Ivan will have the first question ready.
Okay, so here it goes. So it's a number theory question. And it says that you have positive integers a and b that satisfy a certain equation. ab plus 63 is 20 times their LCM plus 12 times their GCD. So we want to find how many ordered pairs a and b satisfy it.
Yeah. So what poll you want to make?
I think it could be at many competitions. I'd rather ask competitions, probably. Okay. Let's see. So a standard poll, where was it proposed? And our attendees could think what could be the first idea that could be useful for this problem.
So you can enter the poll. Yeah, I think this one, our audience got it right? 10 of them, 48% voted for AMC, and it is from a recent AMC.
Unfortunately, not from 2012. Oh.
I submitted for 2012, but they didn't use it until 2013, I think.
Oh, I think this is 2018, 2019.
Or 2018, yeah.
And we have a first idea from the chat.
63 comes from, that is the 2012 is the 63rd AMC. So all the numbers are for 2012.
Amazing.
So guys, the first idea from the chat is to use that AB is equal to LCM of them times GCD, right?
That's what the problem is about, right? It's about that little property.
So how can we use it here? AB is LCM of two numbers times GCD. Very good to remember.
Well, that's true. Do we need to talk about that?
I mean, it might be good just to highlight why, like, the LCM takes the maximum prime power and the GCD takes the minimum prime power. So when you add those two together, you get the prime powers in both A and B adding up in the way that you want. Something like that.
Yeah.
That's how I remember it.
Okay, so it's P1.
And that exclamation mark is punctuation. It's not factorial.
That's true.
Designed to indicate excitement.
I think it's easier even instead of writing lots of primes, just writing every single prime that happens, right? Don't confuse people with lots of primes. You're just looking at one prime at a time instead of the whole factorization.
You're right, guys. Okay, I started a long formula for no reason. Good. So what do we do next? Some people in the chat say SFFT. What does SFFT mean?
They call it Simon's favorite whatever trick. I never understand why do they even give a name for this thing.
So actually, the story of this dates back to an AOPS post in 2003, where Simon Rubinstein Salzito, aka Complex Zeta on AOPS, responded to a math counts a problem, which is like, this is Simon's favorite factoring trick, and everyone's like, who's Simon? And he said, I'm Simon, and this is my trick. And that's how SFFT was born.
I see. So we can just let LCM AB equal to X and the GCD AB equal to Y, and then the whole thing becomes Y.
xy plus 63 is equal to 20x plus 12y, right?
Yeah. And then you can factor whatever way you want to factor, right?
So x minus 12, y minus 20, and I believe it's 177, which is 3 times 59.
Yeah.
It's a prime factor.
40 minus 63. Yeah.
So then you might think, well, I have two solutions, right? X is equal to, or how many solutions do we get, guys?
Well, it depends. Well, are you talking about just the original equation? If it's just the original equation, then you should only have 4 because the factors can't be negative. If they're negative, then x and y are also negative, which is bad because of the minus 59 or the minus 177.
Okay, so x is 71, y is equal to 15, and the second one, x is equal to what? 177 plus 12, which is 189. Fix my algebra if it's not correct, and 1 plus 20, 21.
Yeah.
Okay.
So the GCD and LCM are equal to that, right?
Right, so we have what? That's not right. Some people say that's not right.
Yeah, y should be 23.
Thank you. Yeah, this is 23, yes.
No, I think y, because you said x minus 12 equals, oh no, okay, yeah. Wait, I might have messed, yeah, y should be 23, yep.
So should we say the two possible pairs are 71, 23, and 189 and 21?
No, but that's the LCM and the GCD. That's not original A and B, right?
Yes, it's LCM and GCD.
So something should be true about GCD and LCM. GCD
Right.
always
divides, right? Yeah.
Right. So this goes away, and this is the only possibility, right?
Yeah.
So you find LCM and GCD, okay, and then you need to find A and B from there, right? So there are two possible pairs.
So one is 21A, one is 21B, right?
So
yeah, the GCD is 21 and the LCM is 189.
Yeah, I should not use A and B. That's original variable.
Oh yeah, good point.
21N.
Good point.
21M and 21N.
Yeah.
That's
sure, yeah.
So A is 21M and B is equal to 21N.
Right.
And N is 9.
Yeah. So the only possibility is 1 and 9, right?
Yes.
Yeah, it's LCM M and N. Yeah, equals 9.
21 times 9 and 21, and it's permuted and vice versa, right?
Yeah.
You cannot have 3 and 3, or 9 and 3. Yeah, that's not possible.
Yeah.
Okay, so we have a warm up. We can move on, right? So now we all learned where that Simon's favorite trick come from. Yeah, I never understand where's the Simon about, you know?
Okay, second problem, guys. And again, you can try to do it ahead of us. It's about sets. Maybe David, you can read the problem for us if you see.
Sure. Define a triple A, B, C of sets to be minimally intersecting if the cardinality of A intersect B is equal to the cardinality of B intersect C is equal to the cardinality of C intersect A, all equal to 1, and A, B, and C or A intersect B intersect C is the empty set. Compute the number of minimally intersecting ordered triples of sets for which each set is a subset of 1, 2, 3, 4, 5, 6, 7.
So what do you guys think? Who did propose this problem? It still could be James, it still could be Evan Chan. We might discuss their problems. Is it a random guessing? I don't know.
It's even distribution. Everybody got 2 votes.
Okay. I'm gonna stop it.
So the winner is Yannick, but actually it should be Chris, right?
Yep. Hey,
So where is this problem for?
it was an Amy problem in 2010. And I actually remember very vividly how and where I got the idea for this. I think I was sort of inspired to write some sort of counting argument, enumeration kind of counting problem. And I thought about like the classic 3 Venn diagram, 3 nice circles intersecting in all possible ways, like that you see for the principle of inclusion exclusion. And then I thought, well, what if you had each pair of sets intersecting in just one, element, but then all 3 of them that they didn't intersect at all. And then I decided. So I sort of thought of what the picture would look like.
So we should still start with that Venn diagram, right? For this problem. Then you have an idea what to do. That's a very, the 3 disks.
Yeah, so this was one where I got the picture in mind, and then I came up with the problem too.
Right. So in the center, that little area, you don't have anything.
Right.
Right?
Okay,
so you can block that out.
Okay.
And then you put in X, Y, Z into one of those each.
Yep.
There should be an element here, an element here, an element here. Okay.
Yeah, and that's basically what you want for this set, right?
Yes.
So when you start computing, you should probably use the restrictions, right, first, somehow. How do you make sure each intersection has exactly one element?
Well, you throw elements in there, right? It's easier that way, right?
I mean, you can pick the element X, Y, and Z.
Right. So so the answer is already a multiple of 7 times 6 times 5.
Oh, look, it's an Amy question. That narrows it down significantly.
Well, except maybe modified because,
it will be go over, right? Yeah.
Ivan, you might want to label those sets A, B, and C, so we can refer back to them.
Yeah, because they are different, so that's why we don't divide anything.
So we first pick these 3 values, okay?
Yeah.
Yeah, so pick what goes in A intersect C, then what goes in A intersect B, and what goes in B intersect C.
Yes.
So that's our 7 times 6 times 5.
And then what? We have also the whole set. Don't forget that it doesn't have to be everything.
Yep.
So now you have 4 elements left, and there are 4 spots to put them. Right. So it's just a matter of, I think, you could probably case on like the distribution somehow, like 4 is 0, like.
I look at it this way: we have 4 elements from that set that we haven't placed anywhere, right? So if we think about it element by element, the fate of each element, there are 4 different possible outcomes. It goes in A only, it goes in B only, it goes in C only, and then what's the 4th one?
D only, because D represents a big set.
It goes in nothing, none of those. Yeah.
Okay. So I would rather name them with Latin as regions. 1, 2.
Oh, good, yeah.
3 and 4 possible regions. So if you're left with some 4 elements, say 2, 4, 5, 7, then each of them will have 4 choices. So 4 to the 4. So that would be my answer.
Yeah.
That'd be I think that's larger than 1,000.
What is?
210 times 2056. Yeah, that's 512256. So it's 53760.
Yep. Sounds right.
Yannick, you're faster than I can write. That's cool. I can see Mavcount's school here. Yeah, that's cool. Yeah. Good, guys. So that's.
I suppose if you wanted to multiply that in a way that was least error prone, you could group together like the factors of 5 and, well, you just have one factor of 5, and so you only have 110, I guess. So
Yeah.
Where do things go wrong? Things go wrong in a very bad way.
Wait, we did something wrong?
No.
Oh, it's order
Just
triples.
saying that. Yeah.
Yeah, it's all right. We didn't overcount. Yeah.
I think originally it asked like modulo 1000 or something.
Yeah. Find the last 3 digits of the number of. We joke sometimes it's an Amy problem, so we have to make it twice as long so that we can, constrain the answer format to be a 3-digit number. That is an interesting idea. What if it was unordered triples? I mean, we won't that's something for people to think of offline. You could also, I suppose, think of like, what if there were more sets, like 4 sets, 5 sets, n sets? What would that?
Oh, yeah.
It's not a very hard generalization, but you could think about.
Yeah, I was actually not saying that. I was legitimately confused for a sec because I thought that somehow if you had like if you put 2 elements in the 2, then you might have to worry about like ordering and stuff. But since we were working on each element individually, it's actually okay.
Yeah.
As you can tell, combinatorics is not my strong suit.
Yeah, so each triple will be there 6 times, right? Yeah. Good. Okay, I will ask chat to stop spamming some unrelated things. You're welcome to meet each other, talk to each other.
Well, that's what you get when you turn chat on.
Yeah, maybe you recognize itself from competitions. Maybe you meet in real life. But the next problem is about cookies.
So we are reading the Cookie Monster again. Alex, you want to read the question?
Sure. Yes, so the question is, Cookie Monster says a positive integer n is crunchy if there exist 2 times n real numbers, x1, x2 to x to 2n, not all equal, such that the sum of any n of the xi's is equal to the product of the other n. Help Cookie Monster determine all crunchy integers.
All right. Anyway, I think people may remember like something like this. I think 3 episodes ago, we talked about a problem where we have four integers where the sum of any 2 is equal to the product of 2. Well, this is the generalizations I promised. This problem in fact appeared in, I think, Elmo 2016, where Elmo that year. I should talk about what Elmo means first. So Elmo is like this math Olympia that is held within the math Olympia program, MOP, every year. I think it started like before 2000s. It was
1996 or 5.
Okay, yeah.
And I know that the database in AOPS goes back to 99, I think, but there's also like a huge gap in the mid 2000s where like none of the problems show up. So
I think it was in 98 actually. I might have a paper copy of it, but anyway, yeah.
Yeah. Anyway, so originally it started as experimental Lincoln Math Olympiad because back then MOP was held in Lincoln, and that I don't know if it's every year since then, but what for as long as I can remember, Elmo has gone as a different acronym every year.
Yes. So I have a list of that.
Yeah. I think it's also on like Evan's website or whatever. So like in 2016, the acronym is Elmo lives mostly outside. So it's like a acronym or something like that. Where just like, well, it's Elmo. So everything is related to Sesame Street, and of course the flavor text is written to fit that theme. Yeah. So anyway, anyway, like as you can see, like the problem is clearly generalized from like the EMCC problem that I wrote earlier that year. I mean, it's just like after the contest, I thought about how, like, if I can generalize this problem, and I realized like the approaches actually work. So, well, here it is. I think I like proposed both problems, both versions, because like I assume that there will be. I don't think there was anyone who will attend both competitions, but I'm not sure if that's going to be true in the future. So be careful when you do something like that. Anyway, let's.
But Yannick, we did the problem with what? With 4 of them, right?
Yeah, with 4 numbers. Yeah.
And I don't have an idea how that would help us to do it for 2n. Like,
All right.
Well, you try 6 numbers, you will have an idea, right? What does it look like?
Okay.
You really strictly stick with the definition.
Yeah.
Then you have the idea.
Yeah. Actually, can I share my stuff? I don't think I share for some reason.
Yvonne, can you add screen sharing?
I don't know how to do this, guys. I'm looking and things are different to me than the last time.
While they're figuring that out, I like that the problem says to help Cookie Monster. It's not asking a question; it's just help Cookie Monster. So
yeah, I think all of the problems are phrased that way that year. It's like I don't know, help Elmo prove this thing, and then. Yeah.
I think there's also a thing where, like, if you sometimes take Chinese math Olympiad problems and you translate them to English, it'll like, please determine the number of good integers and the number of bad integers. Yeah. I've seen that once on a China TST 2006 problem. Where it says,
you cannot do the share screen, Ivan. You can just be the hand of what we're talking about.
Yeah, sure. That also work. I can just talk about some of the things we can do. Yeah.
It's trendy, guys, because maybe their update that was recent changed things. I don't see.
Yeah, it's fine. Well, let's get some obvious things out of the way. What happens when n equals 1?
When one of them is 1?
When n equals 1.
N is equal to 1.
Yeah. That's
So the sum of one number is equal to the product of the other number. So which means that the 2 numbers must be equal. So that's not good. Yeah. So let's just get that out of the way, because, well, it's a small case, and yeah. And so n equals 1 doesn't work. We know that n equals 2 works. Let's think about what happens for n equals 3.
What was our answer for n is equal to 2?
I think -1, -1, -1, 2.
Okay.
Yeah. Let's try n equals 3. Oh wait, n equals 1, it's just x1 equals x2, because the sum of one number is equal to the product of the other number.
Your initial equation is wrong, Ivan. It should be x1 equals x2 is the equation.
Yeah.
Wait, sorry.
So the sum of any one of the x1s, so i.e. x1, equals the product of the other one, i.e. x2. So x1 equals x2.
Yeah,
got it.
It's a little bit too stupid, but it's a case that I think we need to handle. Anyway, let's move on to so n equals 2 is good. N equals 3. If I might, why don't we just write down 2 equations again? Just two of them.
2 of them.
Yeah, just any 2 that you find.
Follow the definition.
Yeah.
x1, x2, x3 is x4 plus x5 plus x6, right?
Okay, that's one of them. Just try.
x1 and x2 and x4 is x3 plus x5 plus x6. Right. And I will take the difference here.
Yeah, so this is one approach that we did last time, where we just subtract 2 of them.
Yeah.
So x1, x2, x3 minus x4 is x3 minus x4.
And you put them together?
It's x4 minus x3, I believe.
Yeah.
Okay. So x1, x2 minus 1, x3 minus x4 is equal to 0.
Yeah, it should be plus 1, I think.
Yeah, it should be plus 1.
Plus 1, yeah. Again, I'm losing the sign. So the condition is either x3 is equal to x4 or x1, x2 is equal to negative 1, right?
Yeah,
Yeah.
I think at this point the key is you try to understand the symmetry, because you definitely know some numbers are not equal. So you want to make sure you pick that pair that is not equal and ask yourself, you know, why it's only for example, if you look at the thing over here, you see, for example, you pick up two numbers, x3, x4, they are not equal to 0. And then you ask yourself, why only x1 times x2 shows up, right? Can it be other numbers? It's all about how to read this equation.
I mean, the nice thing about the equation is like the 3 and 4 are separate from the 1 and 2, right?
Yeah.
So
One and two is
Also
nothing
gets, I think that
special,
gets
right?
you. I think that gets you every other pair has the product equal to -1.
Exactly.
Like you clearly get
Yeah,
x. You can clearly repeat this and get x5, x6, but I think you can get every other pair as well.
Yeah,
I think
because
it's more important to even just think about x1, x5, right?
Yeah.
Replaced by two, replace x2.
So
Yeah.
it's kind of
No, write it underneath there. It's better to compare.
x1,
This is
x5.
true. No. Underneath that equation over there. You have that
Here,
equation, right? Yeah. So replace that equation. It could be what?
yeah, x1, x5 that work.
Right. So what does this mean?
so we can assume x3 is not equal to x4, right?
Right. So you start with that assumption, right? You pick up a pair of numbers that is not equal.
Yeah, say these are these. Then we get here, so x1, x5 is also -1. And we can pick for x1 any number, 5, 6, and so on, right? So pretty much from here we get that what? x5 is x6?
Is equal to x6 is
Equal
equal to x2.
right?
Oh, that's just really bad.
Equal to x2 equal to
X1.
x1.
it's also equal to x1
It's also x1.
because the label.
Because you can pair up x1 with x2, x2 with x5, and x5 back to x1.
Sure. Yeah,
Sure.
it's just like it, like any two pair of like you can swap.
But it's now you're done. None of this is bad.
To keep understanding this symmetry, right? Any other two numbers can be in there, right? So they have to be all equal.
But how their product can be -1?
They cannot.
Yeah, so
Yeah.
fail.
So this is no good. Yeah.
Okay.
Yeah.
Fail.
But you see how this can just easily generalized, right? Because like now that we have done n equals 2 and n equals 3, when n equals 4, we just have that the product of any three numbers is equal to -1. Like other than the two that are different.
Yeah.
Okay, you can make all those -1 if you really want.
Yeah.
Now it should be better, right? Because if n is equal to 4, we'll have x1, x1, x2, x3, and there will be x4 plus 1, and there will be x4 minus x5 is equal to 0, right? And then you get that this product, x1, x2, x3, is equal to -1.
Just any product, like all of the six numbers, x1, x2, x3, x6, 6, x8, 7, x8, the product of any three of them is -1.
Yvonne, you're going to need to push up the paper.
Equal to 5, right? Yeah. You start with that pair that is not equal.
But then, which means all of them are equal to each other, but they can be -1, right?
Yeah. And in
x4
fact,
and x5 should need to equal to one of them too, because you cannot have three distinct numbers, right? Basically.
Yeah. Like basically, like you can assume that x4 is not equal to or x4 is not equal to x3, for example. Yeah, because like not both x4 and x5.
X3.
If x4 is equal to x3,
then you go x1, x2, x5 is -1. So pretty much from here, everything is equal to each other except
one of them.
Except one number.
Except one number. Except one number. So all of them can be -1, which is good.
Yeah.
because even product. And this except one number, what it should be?
Let's see. So let's say the sum involved is, if it's sum of n negative 1, then it's negative n is equal to negative 1 to the m. Yeah, it is equal to negative 1 to the n minus 1 times the last number.
Okay, so x times negative 1 to the n minus
1.
Just 1 because n is odd.
Wait.
No, you don't.
As even. So it's x times negative 1.
Oh,
to the
right.
n
is n is even, so n minus 1 is odd.
It's equal to
right.
negative
Okay.
1
Yeah,
times n. So that gives you x equals to n, and then you can calculate.
That's the thing I was thinking was positive. My bad. Yeah. Okay.
And then if you want to check the other way,
n is even in
just write out the numbers, all negative ones, and the last one is n, right?
Yeah.
Yes.
And you can check easily.
And the other way is n minus 1, and then versus negative 1 to the n. So both of them are 1, so that will still work.
Yes.
Yeah.
Okay, so n and the rest of them are negative ones.
Yeah.
Okay, so 2n such numbers, 2n numbers.
Yeah. So now that we have worked through n equals 3 and n equals 4, like it's not hard to just generalize to all the even, and we can show that only the even numbers work. Yeah. And also, we mentioned there's like a different approach for n equals 2, where we like wrote down the two opposites, like instead of writing down x1, x2, x4 equals to x3 plus x5 plus x6, we can write down the exact opposite. So x4, x5, x6 equal to x1 plus x2 plus x3. So we can also do that. Yeah. So the first equation remains the same. The second equation is the exact opposite. We can also do that.
Okay, wait, Jan, do you want me to write anything?
Yeah, sure. So just write down x1, x2, x3. This is the second solution, of course. Equal to x4 plus x5 plus x6.
Yes.
And then we write down the opposite. So x4 plus x5, x6 equal to x1 plus x2 plus x3. Yeah. So now we can just like look at these two again. So if we multiply these two equations together, we get that the product of two sums.
So they're all products. Is the product of two sums.
Yeah. And then we also know that the sum of the two sums is, well, of course, the sum of all numbers.
You mean add them?
No, I mean, I think it just means if you let let A equal x1 plus x2 plus x3, and B equal x4 plus x5.
Yeah, this is his roots approach.
Then it's kind of like, you know that for all choices of like the indices, A times B and A plus B are always the same.
Because your left-hand side is fixed.
Yeah, so I guess the point is that like if you take any three sums, the sum of any three numbers and the sum of any three other numbers, the product is always the product of the six numbers, and their sum is always the sum of the six numbers. So no matter how you permute those six numbers, if you break them into two halves, then the sum of the two halves are the two roots of the quadratic equation. Yeah.
So you create this quadratic equation z squared minus what? A plus b?
Z
plus a times.
B. Yeah, where a plus b and a b are fixed over all permutations. So basically the moral of the story is that if you take any three numbers, the sum can only take two values.
Yeah.
And that is like a really strong condition, and that basically tells us that first of all, there can only be two possible values present among all the numbers, because if you have three different values, you can just swap in and out and get three different values. And second of all, one of the value must appear only once, because like once you have only two possible values, it's like simple case, like simple check. and then once again you can finish with as before, except like I guess one small downside of this approach is that you don't know that the one number is -1, but it's still pretty easy. Yeah.
Ivan, to help you to regroup, this is a quadratic equation, right? Right now,
Yes.
it should have only two solutions, right? But somehow your x1 plus x2 plus x3 can have lots of versions, right? Because you can pick any three of your 6 numbers, right?
Yeah. So, like in that proof, these are kind of same set, right? For
Yes.
any for any choice of indices. Yeah.
A and B, sure, whatever.
Say, for example, x1 plus x2 plus x4, and others.
X3 plus x5 plus x6. Yeah.
Yeah, and along with any other permutations. So the point is that if you take any 3 numbers, the sum can only take one of 2 values.
Yes.
And then if there are like so that implies that there can be only 2 values present among all the 6 numbers.
Sum of any 3 in our case numbers, but in general case
Is n,
and numbers can have only 2 values.
Or I think we can use symmetry again to make the argument instead of writing this kind of sentence. Because all these numbers are symmetric, we can assume x1 is less than or equal to x2, less than or equal to x3, and then so on, right? Because they are all symmetric, right? So clearly we have two possible values, x1 plus x2 plus x3, and then the larger one is x4 plus x5 plus x6. And every other number in between has to take those 2 values, right? So that might help you to make the arguments.
Yeah.
So these are the only 2 values we can have.
So you cannot have 2 strict inequalities. I believe you can claim that.
If you have those, then you have 2 different values, right?
Yeah. More than 2.
Yeah. Then you are good.
Yeah. Nice. Elmo, how many students solved it? Where did you do?
I think the software is pretty good. This was like a problem 1, and like even though I think the participants are all like so quote unquote rookies as are like the first time moppers, but like I think more than like around half or more than half the people solved it. Yeah. So these are problems that were like it's like a practice of like playing around and also like trying to generalize. So it's like it's a fairly easy number 1. I can check if there's data on Evan's website.
Yeah, because when they go to MOB, they have to do pretty good on the JMO or USMO, right? So they should be able to solve this one. But this final approach of understanding the sum and the product is really cool, right? Good way to understand it. So now we have our last question.
I think so.
Okay, guys.
Hey, Ivan.
Long question.
Before we move on to this, can you tend to the Q&A? That I think the chat has kind of gone off the rails.
Yeah.
Q&A.
Yeah. I think you are just
shut off chat
somehow.
Well, I wish I could wait. Give me a second. Chris. Guys in the chat, please stop chatting. I'll start banning people. I already banned a few of you guys. I'll ban more, okay? And because I don't have right now to change the webinar.
I changed.
Yeah, people say they can't concentrate, so.
I think you
I
need
think
to
I
go.
changed it.
Yes.
Okay. Okay. So let's go ahead with this problem now.
Or maybe I didn't have that option. Maybe Zooming, you have the control. But then you can even ask, let Yannick to share his things too. Good, guys. Next problem. So we have 8 points equally spaced on a circle, right? And we pick point P inside it. Think of it like a pizza, right? You pick point P, and you draw these segments to some of the vertices, and you know that the area of segment PA1, A2 is 1/7, segment PA3, A4 is, this region is 1/9. What we want to find is what is the area of this region over here. Yannick, have you seen this problem? Alex, did you graduate before?
The numbers look a little bit familiar.
I remember test solving this. This was a very interesting one. Because I remember when I first saw it, like when I was first reviewing the packets, the original solution to this problem was like a page and a half long. Now, granted, this is Amy style page and a half long, so it's not really a page and a half long, but I was still very motivated to try to find a simpler solution. So that's how I got to work on this problem.
Yeah, I think I remember this problem now. It's pretty interesting. I forgot which year it was. I may have done it in contest.
I think, if I remember correctly, it was last year.
Oh,
2019.
Oh, then I did it during my whatever live solve that I did last year. I was like doing something crazy last year where I like solved both AMVs in, try to solve both AMVs in 3 hours or something like that. But that
yeah, I saw your challenge. You timed yourself for how many? 3 hours?
3 hours for both AMVs and 75 minutes for all 4 AMCs. They didn't go well.
Okay, guys. So before we go to the solution, I can tell you where the problem came from, where this idea comes from.
Yeah, this one has some classical background.
Yes. So there is a famous pizza theorem. You can Wikipedia it. And one day I was at Zooming's house and I was looking in one of the books, and I found that there is a second pizza theorem problem. And it says the following.
Your screen's a little low. You might want to move it up a little bit.
Yeah, thank you. Thank you, David. Let me take a pen that writes. So what does it say? Suppose we pick even number of points that are equidistant on a circle, equidistant, that's the key, and we pick any point P, and we connect the dots. Then, if you color alter in alternative way, the dark areas add up, have the same area as the white areas. So this is the fact that I read, and I was really surprised why it's true. And I had nothing to do. Well, I thought, let me try to solve this, right? And this is true for what? Any even number. Here we have 6 pieces, 6 dots. You can make it 4, 6, 8. 2 also makes sense, right? And so on, right? So I will start thinking it. I didn't look at the solution first. And I suggest you guys also to start thinking about this problem. Why it's true.
I mean, it's the same thing that we'll cover when we solve the other problem, right?
Yes, you can see how I did.
Sounds very cryptic, but I guess you won't think about it for that long if you're going to listen to the rest of the show.
Well, let's start. I started with the 4 equally spaced. I thought, okay, maybe I don't see something for n. Let me start with 4. Why, if we do it with 4, let's make it not symmetric. Why, if we do it with 4, the sum of these 2 black areas is the sum of the 2 white areas?
Well, I think it becomes infinitely less, what's the word? Scary? Intimidating? Intimidating is the word. If you restrict yourselves to not looking at the areas of the sectors, but rather the areas of the triangles. So if you draw the actual foregon, and you might want to move your paper up a little more. Yes, if you draw the foregon, or the square rather, the square, that's the technical term.
You want to take care of the arcs that you don't like, right?
Yes,
and they are gone. And then the only thing you want to compute is the triangle.
And I think this is actually decently well known. I'm not sure about this though. It basically says that the sum of the areas of the 2 white triangles is the same as the sum of the areas of the 2 shaded triangles, and I'm fairly certain this is well known.
Yeah.
For some definition of well known.
Well, that's clearly true because they have the equal base, and then the height is the same, right? If you add them up.
Yeah, sure.
Right. So the coolest part of this problem is you have to use that they're the same equally spaced, and you have to count this crust that kind of. It's really hard to compare these circular, right, regions here. But once you take them off, what you want to show is some of these black is some of these white, which is fine because the bases are the same and the altitude is the distance between 2 parallel lines, right?
Yeah.
But this doesn't work as well when we get to a hexagon.
It doesn't?
It still works decently okay. You just have to be a little. It's just not as clear.
First, what happened?
Wait, is it true for a hexagon? I'm not sure, guys. Wait, I think.
It's true. It's true. It's obviously true because the pizza theorem is true. So
right.
It can't be false. But it's a lot harder to show that those 3 areas add up to half of the hexagon.
But then you can use angles, right? Or no? No, not angles.
I think it's easier to use so because all the bases are the same, it's essentially equivalent to showing that the sum of the heights to odd guys is the same as the sum of the heights to even guys. Yeah. And I think you can do this by
just extending to equilateral triangle and use area argument. I think that will work.
Yeah.
You can also exploit linearity, I think.
Yeah, if you extend, you get equilateral triangle, and sum of the distances to the equilateral triangle, which are the same, right?
Oh no, you can just use the fact that in a hexagon, the sum of the distance between any 2 pair of opposite sides is the same. I think that should work. Wait, no, that doesn't quite work.
No, it doesn't work that way because these 3 are not paired in that way.
Right.
Yeah.
But Yannick's idea, it makes sense. You just complete the picture with 2 equilateral triangles which are congruent because it's a regular polygon, and sum of the distances to from any point inside the equilateral triangle is the same, right?
The area of the triangle when the triangles are congruent, so they have the same area.
So and that applies to any applies to any even polygons, right? Regular, because
yes, it does.
Yes, by the area, because of the area argument. The base is the same, the area is the same. It means sum of the distances is the same. Yeah. So that's what.
Wait a minute.
Wait. So the way you do this is you extend sides until you have. Just say you start with like a 2n-gon, right?
Let's draw octagon and see if it works that way. Your argument.
Well, for octagon, this argument works.
But the other argument should also work, where you draw a square.
You want to generalize it, right? Yeah.
Okay, I can draw an octagon. It's not a problem. Okay.
So then you draw 2 squares, I think.
Yeah. So with a general 2n, with an octagon, you can extend the sides twice to get 2 squares, and those squares are congruent.
Yeah.
So your argument still works.
Yeah.
I agree. Yeah. Nice. Yeah, makes sense. So sum of these distances is fixed, right?
You want the horizontal
You
guy.
mix them up, Ivan.
My bad, guys. My bad. So ignore this one.
Yeah, the sum of those distances are the same.
Yes.
Because the bases are the same, because everything's right.
So that's how I thought about this problem. I thought I give some areas for the students and let them figure out the rest. So I thought this is cool, and I think I played with a hexagon, but with an octagon I thought it was cooler because look, I started with 1/7, 1/9. Then I immediately know, for example, this area X, if I draw this one and I draw this one, right? They add up to 1/8, 1/4. Does it make sense? Mm-hmm. The two opposite ones end up to 1/1/4 of the area of the full circle, right? Because they have the same crust pieces, and these two are parallel, and this. Mm-hmm. So that would be 1/4 minus x. That was my thought, right? Alex, does it make sense what I'm saying, or it's not?
Yeah.
Okay.
The opposites ones add up to 1/4 because, the heights add up to the same height.
Because if something is not clear in my explanation, please let me know. And then I thought, well, they can find this area because pretty much it is fixed. Because if I know it's 1/7, so the triangle will be 1 minus 7 minus this crust, and this is 1/9 minus this crust, right? So this will be 1/4 minus x minus the crust again, right? If we talk about triangular regions. And for this triangle, if I know the side lengths, I know this altitude, I know this altitude, I know this area, the red area. So the altitude in the white triangle was kind of determined. And that was how I thought about this problem. It's not a solution. The solution was very long.
I mean, you're basically done at this point, I think. You have to be a little careful, but you can probably do it with not too much effort. I'm not sure. Maybe there's some technical arguments that you have to finesse with, but.
Okay, so
I remember when I was live solving, I thought about use more coordinate approach, because I know that for example, the area of A1, A2, P only really depends on the y coordinate of P, and A3, A4, P only depends on the x coordinate of P. So up to some scaling, you can basically compute the coordinate of P, and then use that to see how far off are you from the 1/8, the
origin.
Origin, yeah.
Yeah. Basically, you can compute the coordinates of P.
Mm-hmm. With some very annoying scaling factors that you may have to just ignore and then reason out afterwards. But I think it's doable.
And I think this is the shortest solution that we are talking about. So I can explain what you just said. So the shortest solution goes as follows. We ignore everything. We set up coordinates.
Do you want to move the paper up? Yep.
And we will say this region is 1/7, and 1 unit in our coordinate plane will be equivalent to what, Yannick? To the change in the area to the change in area of a triangle. Say this is the origin, O01, O2, in area equal to 1. So for example, if this is the origin and I lift this and I go 1 unit down, the area of the new triangle, A1 to this point, which is 0, -1, to this point A2 will be 1 unit bigger than A1 O A2.
Yeah.
It's basically just normal coordinates except with the scaling factor based on the length of the base, I think.
Yes. So
you're just re-raising in terms of areas. You're just re-normalizing in terms of areas to make the thing easier to work with.
It's very barycentric.
Yeah, so this coordinate P, if this area is 1/7, at O we get exactly 1/8, right? So you can actually look at the difference. It's going to be 1/7 minus 1/8. So we are that much down. 1 minus 1/7 will be 1/56 down, right? Negative 1/56.
And it's not 0 because you are moving P in. So P has a positive X coordinates.
And I'm moving P in. I move where P? This is 1/9, so I move along this direction.
1/72, 1/72.
1/72, right?
Yeah.
Which is 1/8 minus 1/9.
Yeah.
So, okay. It's an ugly, sorry, I made the diagram very ugly, but these are all coordinates, right, of this point P. And now the most interesting thing, how do you compute what is that area?
Yeah.
So what do you do, guys?
Well, it's the length of the perpendicular relative to P to A6, A7, right? So you have to drop both the perpendiculars to...
I think you just drop, you try to drop both perpendiculars and you note that the change is going to be something related to the change in the X and Y coordinates times like √2 or times 1/√2 or something like that.
Yeah, so you want to know how much this area changed. So you'd rather draw this parallel line to A7, A6, right? So if I change the diagram, this is the line that we draw, right?
Yeah.
So we know our coordinates are 1/72, negative 1/56. And here there is no change going along this line, no change. So how much you change is the distance from point P to the line x plus y is equal to 0, right?
Yeah.
That should just be 1/72 minus 1/56 times √2 divided by √2.
Divided by √2.
Yeah.
Minus, sorry?
1/56.
Uh-huh.
So that's going to be negative, but whatever.
Absolutely.
And then
It's supposed to be negative, yes.
divided by √2.
Yeah. That's the distance from that point to the line.
Yes.
So this will be 1/8 minus the area of we are looking for A7, P, A8, right? And
Yeah, I think so.
the question that Amy asked for that now.
Sure. Or whatever.
Yeah. That seems
we don't worry about science because it's Amy.
It's the other way around. Yeah, the actual answer should be absolute value.
Yeah.
Yeah, but regardless, it's Amy, and they give us science already. So,
I mean, you just take the absolute values at the end of everything when you're done.
Yeah,
So,
yeah.
as long as you're careful not to mess up in the middle, where you're like taking a negative, so you're like adding things unnecessarily, you should be fine.
Yeah, so nice pizza problem. Yeah.
Very good. So we are exactly at 9 o'clock. We complete our 4 questions, right? So we will end the meeting here. Everybody have a good night.
You too.
Night.
Right.